Text and code embeddings by contrastive pre-training Arvind Neelakantan *1 Dalzu *1 Rahul Puri 1 Alec Radford 1 Jesse Michael Han 1 Jerry Torik 1 Chiming Yuan 1 Nicholas Tezak 1 Joras Wook Kim 1 Chris Holasi 1 Johannes Heidek 1 Pranav Shyam 1 Boris Power 1 Tina Ilaundu Nekal 1 Gayarish Sastry 1 Gretchen Kruger 1 David Schnur 1 Felipe Petruski Such 1 Kenny HSU 1 Madeleine Thompson 1 Tabarak Khan 1 Toki Sherbakov 1 Joanne Zhang 1 Peter Welinda 1 Lillian Wing 1 Abstract 1 Introduction. Deep unsupervised learning with generative and embedding models has seen dramatic success in the past few years. Generative models, Peters et al., 2018, Raffel et al., 2019, Van den Orde et al., 2016, Ramesh et al., 2021, Brown et al., 2020, Chen et al., 2021, are trained to max *= contribution 1 OpenAI. Correspondence to Arvind Neelakantan, Arvind at openai.com. 70 average performance vs model size 68 performance. Text embeddings are useful features in many applications such as semantic search and computing text similarity. Previous work typically trains models customized for different use cases, varying in dataset choice, training objective and model architecture. In this work, we show that contrastive pre-training on unsupervised data at scale leads to high-quality vector representations of text and code. The same unsupervised text embeddings that achieve new state-of-the-art results in linear probe classification also display impressive semantic search capabilities and sometimes even perform competitively with fine-tuned models. On linear probe classification accuracy averaging over 7 tasks, our best unsupervised model achieves a relative improvement of 4% and 1.8% over previous best unsupervised and supervised text embedding models respectively. The same text embeddings when evaluated on large-scale semantic search attains a relative improvement of 23.4%, 14.7%, and 10.6% over previous best unsupervised methods on MSMARCO, NaturalQuestions and TriviaQA benchmarks, respectively. Similarly to text embeddings, we train code embedding models on text, code, pairs, obtaining a 20.8% relative improvement over prior best work on code search. 66, 64, 62, 60 S300 mm 1.2 BL6B model size XL175B Figure 1. Average performance of unsupervised capped-in-text models of different sizes across 22 tasks consisting of linear probe classification, text search, and sentence similarity tasks. Implies the likelihood of observed data while embedding models are trained to distinguish observed data from noise. Son, 2016, Van den Orde et al., 2018, Radford et al., 2021, Chia et al., 2021, Gao et al., 2021, Isaac et al., 2021. Generative models have been shown to produce realistic content and benefit many downstream applications, reducing the need for labeled training datasets. In generative models, the information about the input is typically distributed over multiple hidden states of the model. While some generative models, Kingma and Welling, 2014, Quiroz et al., 2015, can learn a single representation of the input, most autoregressive transformer, Vaswani et al., 2017, models do not, Raffel et al., 2019, Brown et al., 2020, Chen et al., 2021, Ramesh et al., 2021. However, learning such a representation, or embedding, is necessary for many tasks. Systems that search over millions or billions of items require each entry to be embedded as a dense representation and build an index in advance to save computational costs at query time. These embeddings are useful features for classification tasks and can also enable data visualization applications via techniques such as clustering. Embedding models are explicitly optimized to learn a low-dimensional representation that captures the semantic meaning of the input. Radford et al. 2021, Chia et al. 2021, George I et al. 2020, Gao et al. 2021, Isaac Ard et al. 2021. Text and code embeddings by contrastive pre-training. In this work, we train embedding models using a contrastive learning objective within batch negatives. Son, 2016, Yi et al. 2011, on unlabeled data. The input is encoded with a transformer encoder, Vaswani et al. 2017, and we leverage naturally occurring paired data to construct training data with no explicit labels. Text embedding models are trained on paired text data where we consider neighboring pieces of text on the internet as positive pairs. Code embedding models treat the top-level docstring in a function along with its implementation as a text code pair. The training signal of the contrastive objective on its own is not sufficient to learn useful representations, and we overcome this by initializing our model with other pre-trained models. Brown et al. 2020, Chen et al. 2021. Finally, we find that it is critical to use a sufficiently large batch to achieve the optimal performance. We show that this simple recipe combining pre-trained model initialization, large batch contrastive learning and training at scale, can produce text and code embeddings that possess a broad range of capabilities. We train a series of unsupervised text embedding models, capped in text, of different sizes, ranging from 300M to 175B parameters, and observe a consistent performance improvement with increasing model sizes. Figure 1. On classification accuracy averaging across 7 linear probe classification tasks in Centival, Caneo and CLO, 2018, our largest unsupervised model achieves new state-of-the-art results with a relative improvement of 4% and 1.8% over the previous best unsupervised, George I et al. 2020, and supervised, Gao et al. 2021, text embedding models, respectively. Text embedding in previous work was studied under different domains, varying in data, training objective and model architecture. Precisely, sentence embedding, Reimers and Gavike, 2019, Gao et al. 2021, George I et al. 2020, and neural information retrieval, Li et al., Guu et al. 2020, Karpukhin et al. 2020a, Sachan et al. 2021, Isaac Ard et al. 2021, have remained different research topics evaluated on distinct benchmarks, even though both aim to learn high-quality text representation. However, we find the same model that achieves good performance on sentence embedding benchmarks, as discussed above, is also able to obtain impressive results on large-scale information retrieval. When evaluated on the MSMARCO passage ranking task, Nguyen et al. 2016, to search over 4M passages, capped in text gets a relative improvement of 23.4% over previous best unsupervised methods, Robertson, 2009. On the task of searching on 21M documents from Wikipedia, capped in text obtains a relative improvement of 14.7%, and 10.6% over previous unsupervised methods, Isaac Ard et al. 2021. For natural questions, Kwiatkowski et al. 2019, and TriviaQA, Joshi et al., 2017, respectively. On TriviaQA, our unsupervised method is even competitive with fine-tuned models. Next, we train code embedding models, capped in code, using the same recipe. Our models learn via text, code, pairs, extracted from open source code. We evaluate our model on CodeSearch.net, Resultsin et al., 2020, a commonly used code search benchmark, where the task is to find the most relevant code snippet given a natural language query. Our models achieve new state-of-the-art results with a 20.8% relative improvement over the previous best result, Gyo et al., 2021. Unlike text embedding models, we observe no performance improvement on code search when increasing the number of parameters of capped in code from 300M to 1.2B. Finally, we experiment with fine-tuning our models on several supervised datasets and study the transfer learning performance. When fine-tuned on NLI, natural language inference, datasets, we see a further boost in linear probe classification, outperforming the previous best transfer method, Gao et al., 2021, by 2.2%. On SST2 sentiment classification, Soka et al., 2013, we find that our representations are sufficiently descriptive that even a simple KNN classifier achieves results comparable to a linear probe classifier. Interestingly, zero-shot performance with our embeddings outperforms the supervised neural network models introduced along with the release of the SST2 dataset. We also fine-tune the unsupervised model on MSMARCO and evaluate it on a suite of zero-shot search tasks in the B benchmark, Thakur et al., 2021. In the transfer setting, our models achieve a 5.2% relative improvement over previous methods, Isaac et al., 2021, and is comparable even with methods, Santhanam et al., 2021, Formal et al., 2021, Wang et al., 2020, that demand substantially more computation at test time. To approach our models are trained with a contrastive objective on paired data. In this section, we present more details on the model architecture and the training objective. The training set consists of paired samples, 11, y, ni equals 1, where 11, y, corresponds to a positive example pair, indicating that 11 and y are semantically similar or contextually relevant. 2.1 Model given a training pair, x, y, a transformer, Vaswani et al., 2017, encoder E is used to process x and y independently. The encoder maps the input to a dense vector representation or embedding, figure 2. We insert two special token delimiters, SOS, and EOS, to the start and end of the input sequence respectively. The hidden state from the last layer corresponding to the special token, EOS, is considered as the embedding of the input sequence. Text and code embeddings by contrastive pre-training model parameters embed dimensions batch size SML/XL encoder 300M1.2B6B175B1024 2048 4096 12288 12288 6912 5896 4976 encoder input, SOS, EOS, figure 2. The encoder E maps input X to embedding VX. Special tokens, SOS, and EOS, are appended to the start and end of the input sequence respectively. The last layer hidden state corresponding to the token, EOS, is extracted as the embedding of the input sequence. Table 1. Batch size used to train the models of different sizes. Used for unsupervised representation learning in prior work, Radford et al., 2021, Chia et al., 2021, Chen et al., 2020, Isaac Ard et al., 2021. For each example in a mini-batch of M examples, the other, M1, in the batch are used as negative examples. The usage of in-batch negatives enables reuse of computation both in the forward and the backward pass, making training highly efficient. The logits for one batch is a matrix, where each entry logit, 11, yj, is given by logit, 11 yj, equals sim, 11, yj, times exp, to, turn day, j set membership symbol, 1, 2, encoder, EOS, where to is a trainable temperature parameter. Figure 3. The encoder E maps inputs x and y to embeddings, vx and vy independently. The similarity score between x and y is defined as the cosine similarity between these two embedding vectors. The transformer encoder maps the input, x and y, to embeddings, vx and vy respectively, and the similarity between two inputs is quantified by the cosine similarity between their embeddings, vx and vy, figure 3. Vx equals E, SOS, XX, EOS, X, Vy equals E, SOS, YY, EOS, Y, Vx times Vy sim, X, Y, equals Vx times Vy, where is an operation to concatenate two strings together. We found that using different delimiters leads to more stable training. For x, we use as, SOS, x and as, EOS, x, while we use and as, SOS, y and EOS, y respectively for y 2.2. Training objective: the paired samples in the training set are contrasted against in-batch negatives, Yi et al., 2011, Son, 2016. Contrastive learning with in-batch negatives has been widely. Only entries on the diagonal of the matrix are considered positive examples. The final training loss is the sum of the cross-entropy losses on the row and the column direction, as described in the following NumPy-style pseudocode. Labels equals np.arrange, m, l underscore r equals cross underscore entropy, logits, labels, axis equals 0, l underscore c equals cross underscore entropy, logits, labels, axis equals 1, loss equals, l underscore r plus l underscore c, /2. We initialize our models with pre-trained generative language models. Captain text is initialized with GPT models, Brown et al., 2020, and Captain code is initialized with Codex models, Chen et al., 2021. When fine-tuning our models, Section 3, the supervised training data like NLI datasets contain explicit negative examples and they are used along with the in-batch negatives. 3 results: our models are trained on naturally occurring paired data. Captain text models are trained on internet data with neighboring pieces of text as positive pairs for the contrastive objective. The code embedding Captain code models use text, code, pairs extracted from open source code. As discussed in section 3.4.1, sufficiently large batch size is crucial to achieve good performance with our setup. Table 1 lists the batch sizes used to train the models of different sizes. We evaluate our text embedding models on a broad range of tasks: linear probe classification, sentence similarity, and text and code embeddings by contrastive pre-training semantic search. While sentence embedding, Reimers and Gavik, 2019, Gao et al., 2021, George I et al., 2020, methods report results only on embedding benchmarks and neural information retrieval methods, Li et al., Guu et al., 2020, Karpukhin et al., 2020, Sachan et al., 2021, Isaac Ardit al. 2021. Report results only on search benchmarks. We use the same unsupervised model across all these tasks. 3.1 Text embedding the Centival benchmark, Canio and Clo, 2018, is widely adopted to assess the quality of sentence embeddings, consisting of a broad collection of tasks in the categories of linear probe classification and sentence similarity, and we use the same to evaluate ours. 3.1.1 Linear probe classification. When evaluated on linear probe classification, the embeddings are used as features to train a linear classifier to solve a variety of downstream tasks. The results in Table 2 demonstrate a clear advantage of larger model sizes producing better features for improved classification performance. In transfer learning setup, we fine-tune unsupervised captain text models on SNLI, Bowman et al. 2015, and MNLI, Williams et al. 2018, datasets using entailment pairs as positive examples and contradiction pairs as negative examples. On both unsupervised learning and transfer learning settings, we achieve state-of-the-art results. 3.1.3 Sentence similarity. On sentence similarity tasks in Centival, we find that our models perform worse than previous SOTA methods, Table 4. Sentence similarity is not a completely well-defined downstream task. For example, are the sentences, Jack loves Jill and Mary loves chocolates, similar. 1.2 For example, Goodman, 1972, argue that two objects can be infinitely similar or dissimilar, Verbeek et al. 2012. A possible explanation for why our models perform better than prior work on search and classification but not on these tasks is that our models might not be optimized for the specific definition used by these sentence similarity benchmarks. It is important to note that previous embedding search methods do not report performance on sentence similarity tasks. Karpukhin et al. 2028, Sachan et al. 2021, Isaac Ardit et al. 2021. More discussion on this phenomenon is presented in section 3.4.2. 3.2 Text search. Previous work on training embedding methods for search typically requires fine-tuning on a particular text search dataset. Karpukhin et al. 2028, Sachan et al. 2021, Question et al. 2021. It is also common to have a multi-step setup where fine-tuned models rely on an expensive query and document cross-attention encoder in the final step. Question et al. 2021, Wang et al. 2020. In contrast, we push the limits of using a single embedding model for large-scale semantic search. 3.1.2 ZERO, SHOT and KNN classification. In this section, we discuss results using zero-shot classification and k-nearest neighbor classification on the SST2 binary sentiment classification task, Soka et al. 2013. We experiment with 6B.L. captain text model fine-tuned on NLI data for this study. In the first zero-shot experiment, each input text is assigned with one of the two labels, positive, negative, based on which label has its embedding closest to the input text embedding. The performance can be further improved by prompting, where we use a simple label description. This is an example of a positive/negative movie review, instead of a single word. This zero-shot usage of embeddings is novel compared to prior work on embeddings, and it is interesting to note that our zero-shot results are better than the supervised neural network results reported along with the release of the dataset, Soka et al. 2013. In the KNN classification experiment, given an input text, the prediction is the majority label among 256 training examples closest to the test input in the embedding space. As shown in Table 3, the KNN classifier without any task-specific tuning of trainable parameters achieves results comparable to a linear classifier. 3.2.1 large-scale First, we evaluate our models on several large-scale text search benchmarks. MSMARCO, New Unit AL, 2016, requires the model to search over 4M documents, while NaturalQuestions, NQ, Kwiatkowski et al., 2019, and TriviaQA, Joshi et al., 2017, involve searching over 21M Wikipedia documents. We use the face library, Johnson et al., 2019, to build the vector indices for approximate k-nearest neighbor search. The same unsupervised model discussed previously achieves impressive performance on semantic search. Table 5 demonstrates that Captain Text outperforms prior unsupervised approaches by a big margin, and larger model sizes consistently lead to improved performance. Surprisingly, on TriviaQA, our model is even competitive with fine-tuned models. 1 https://yovgo/status/143129964555001114222 https://yovgo/twitter.com/yovgo/status/1483565265755402225 S=20 text and code embeddings by Contrastive pre-training Mr. CR subj unsupervised 86.2 88.6 90.7 94.4 95.4 95.8 mpqasst trick mrpc average. Burt, Devlin et al., 2019, SimCSE, Gao et al., 2021, Dickaluta, George I et al., 2020, 78.7 84.7 85.2 88.7 87.5 88.5 84.4 89.5 90.0 92.8 95.0 93.2 69.4 72.4 74.6 84.9 87.6 88.3 Captain Text S Captain Text M Captain Text L Captain Text XL 87.1 90.1 94.9 88.3 89.0 90.9 96.7 89.6 90.6 92.6 97.0 90.6 92.2 93.5 97.4 91.5 Transfer from NLI data 91.8 93.9 95.3 96.2 95.2 96.6 97.0 97.4 71.6 73.6 73.6 74.1 88.4 89.9 90.9 91.8 Zbert, Reimers and Gavik, 2019, SimCSE, Gao et al., 2021, 84.9 88.4 90.1 92.5 94.5 95.2 90.3 90.1 90.7 93.3 87.4 93.8 75.9 77.7 87.7 90.2 Captain Text S Captain Text M Captain Text L Captain Text XL 87.3 89.8 90.8 92.4 91.0 92.7, 93.5, 93.9, 94.6, 95.7, 96.2, 97.0, 90.5, 91.3, 91.2, 91.8, 91.4, 95.3, 95.7, 95.8, 95.0, 96.6, 96.0, 96.4, 75.6, 76.5, 76.9, 78.1, 89.3, 91.1, 91.5, 92.2. Table 2. Captain text models of different sizes, ranging from 300 ms to 175 xl, are compared to previous work on linear probe classification tasks in Centival. We report performance of unsupervised models, as well as those fine-tuned on NLI data. Method accuracy 0 shot with prompting KNN linear probe full fine-tuned SOTA 88.1, 89.1, 93.3, 95.7, 97.5 MSMARCO NQ TriviaQA fine-tuned SOTA 44.3, 84.8, 89.8, 84.1, 87.8. Table 3. Comparison of different classification strategies using the 6B Captain text model fine-tuned on NLI data for SST2 binary sentiment task, SOCA et al., 2013. Our zero-shot results are better than the 85.4% accuracy obtained by supervised neural networks reported along with the release of the dataset, SOCA et al., 2013. STS-12-13 unsupervised -14-15-16 average sim CSE, Gao et al., 2021. 72.9, 84.0, 75.6, 84.8, 81.8, 79.8. Captain text S62.1, 60.0, 62.0, 71.8, 73.7, 65.9. Captain text M62.7, 62.8, 64.6, 73.9, 75.3, 67.9. Captain text L 62.4, 66.4, 67.6, 76.0, 77.5, 70.0. Captain text XL 64.1, 67.5, 68.4, 76.7, 78.7, 71.1. Transfer from NLI sim CSE, Gao et al., 2021. 77.5, 87.3, 82.4, 86.7, 83.9, 83.6. Captain text S 72.8, 80.6, 78.7, 84.7, 82.0, 79.8. Captain text M 73.7, 80.2, 78.9, 85.0, 82.8, 80.1. Captain text L 71.8, 79.7, 79.0, 85.8, 84.0, 80.1. Captain text XL 72.3, 80.3, 78.9, 85.1, 85.1. 80.3. Table 4. Captain text performs worse than the previous best sentence embedding method on sentence similarity tasks. We investigate this result in more detail in section 3.4.2. Unsupervised BM25 ICT MSS Contriva 18.4, 62.9, 78.3, 50.9, 66.8, 59.8, 74.9, 67.2, 81.3, 76.4, 83.2, 57.5, 73.6, 68.2, 79.4 74.2 83.2 Captain Text S Captain Text M Captain Text L Captain Text XL 19.9 20.6 21.5 22.7 65.5 77.2 68.7 79.6 73.0 83.4 78.8 86.8 75.1 81.7 78.0 83.8 80.0 86.8 82.1 86.9 Table 5. Evaluation of unsupervised Captain Text models of different sizes on several large-scale text search benchmarks. We report MR at 10 on MSMARCO and recall at 20. Recall at 100 for NQ and TriviaQA as done in prior work. Results for training with inverse closed task, ICT, and masked salient spans, MSS, objectives are taken from Sacharnit al. 2021. Captain Text achieves the best results among unsupervised methods, surpassing keyword search methods on MSMARCO, Robertson, 2009. And embedding-based methods, Isaac Ardit al. 2021, on NQ and TriviaQA. Text and code embeddings by Contrastive pre-training 3.2.2. BSIG Next, we evaluate our models on 11 zero-shot search tasks in the B evaluation suite, thatcontrastive al. 2021. First, we observe that our unsupervised model performs competitively even with some previous embedding methods that leverage supervised MSMARCO data, Zierangit al. 2020, Hofstadter et al. 2021. Keyword-based BM25, Robertson, 2009, achieves the best results in the unsupervised setting while Captain Text achieves the best transfer learning results. In the transfer setting, our models achieve a 5.2% relative improvement over the previous best embedding method, Isaac Ardit al. 2021. It also outperforms DocT5 query, Noguera et al. 2019a, that relies on a fine-tuned T5 model, Raffel et al. 2019, for document expansion. Captain Text results are competitive even with methods that use substantially more compute at test time. BM25 plus CE, Wang et al. 2020, uses keyword search to select top 100 documents which are then re-ranked by a cross-attention neural network encoder. The ranking encoder network performs computationally expensive joint query and document attention and cannot exploit indexing and approximate nearest neighbor algorithms for fast and efficient search at query time. Several other existing work take this approach of leveraging more computation resources at query time to obtain better search performance. Colbert v2, Santhanamit al. 2021, is a multivector method that represents the query and the documents as a set of vectors, and employs a multi-step retrieval procedure to obtain relevant documents. Splade v2, Formalit al. 2021, represents queries and documents as sparse vectors of size equivalent to the vocabulary of the BERT encoder, Devlin et al. 2019. Our Captain Text models compute only one dense embedding per document which are indexed offline and does not depend on any cross-attention re-ranker at query time. Embedding models with increased distractors and still don't see bigger models giving a boost in search performance. 3.4 Analysis 3.4.1. Effect of batch size. Our ablation study highlights the effect of the model's batch size on the final performance. Table 9 compares the performance of S300M Captain Text model trained with different batch sizes on the NQ development set. Since we train within batch negatives, a larger batch increases the chances of having hard negatives in a batch, resulting in a significant performance boost. 3.4.2 Training behavior. We observe that as we train our models for longer, the performance on search and classification tasks increases while the performance on sentence similarity tasks decreases. Figure 4. As discussed previously, sentence similarity is not a well-defined task. A hypothesis is that search tasks and sentence similarity tasks might have contradicting definitions. For example, a sentence and its negation could be considered as relevant during search, but not similar in sentence similarity tasks. It is also important to note that previous embedding search methods do not report performance on sentence similarity tasks. Karpukhin et al. 2020a, Sachan et al. 2021, Isaacard et al. 2021, and previous sentence embedding methods do not evaluate on search tasks. Reimers and Gavike, 2019, George et al. 2020, Gao et al. 2021. When deciding the model checkpoints to use for evaluation, we assigned higher importance to search and classification tasks as they are commonly associated with clearly defined real-world applications, while sentence similarity tasks are less so. For related work 3.3. Code search. We evaluate our code embedding models on the code search task using the Code Search Net benchmark, Husin et al. 2020. Given a natural language query, the model is expected to retrieve the relevant code block among 1K candidates. The models are evaluated on 6 programming languages and our model achieves state-of-the-art results. Table 7. Unlike with text embeddings, we do not see a performance improvement with increased model size for code embeddings. We also evaluate on a harder setting of finding the relevant code block among 10K candidates instead of 1K. Here, we compare the performance of capped-in text models against capped-in code models. Table 8. It is interesting to see that text embedding performs fairly well in code search, especially in Python. We see a drop in performance for code. The goal of representation learning, Bengio et al. 2012, is to learn an embedding space in which similar examples stay close to each other while dissimilar ones are far apart. Atscale et al. 2006. In contrastive learning, the learning procedure is formulated as a classification problem given similar and dissimilar candidates. Chopra et al. 2005, Gutman and Hyvarainen, 2010, Schroff et al. 2015, Son, 2016, Van den Orde et al. 2018. Recent work relies on contrastive objective to learn representations for images. Wu et al. 2018, He et al. 2020, Chen et al. 2020, Spontar et al. 2021, Text, or both jointly, Liu et al. 2019, Sun et al. 2019, Kim et al. 2021, Radford et al. 2021, Khosla et al. 2020. In self-supervised contrastive learning, positive samples can be collected in various approaches, including by creating an augmented version of the original input without modifying the semantic meaning. Gao text and code embeddings by contrastive pre-training COVID NFC Fika Argtush Quorus Effect Climate DBP Hotpot Fever Average. Unsupervised BM25, Robertson, 2009, Contriva, Isaacard et al. 2021, 65.6 32.5 23.6 31.5 27.4 31.7 24.5 37.9 36.7 19.3 78.9 83.5 66.5 64.9 21.3 15.5 31.3 60.3 29.2 48.1 75.3 47.6 68.2 40.9 Captain Text S Captain Text M Captain Text L 52.9 32.0 34.1 38.7 21.0 68.1 44.3 34.5 37.3 41.2 23.3 70.3 42.7 36.9 39.7 39.2 22.8 68.7 Transfer from MSMARCO 65.4 68.3 71.2 15.8 15.6 16.1 27.2 51.5 29.6 53.0 31.2 54.3 57.1 42.2 58.2 43.2 63.8 44.2 Tarsby, Hofstadter et al. 2021, Ants, Ziering et al. 2020. Contriver, Isaac Ard et al. 2021. 48.1 31.9 30.0 42.9 65.4 23.7 29.5 41.5 59.6 32.8 32.9 44.6 16.2 24.0 23.0 83.5 85.2 86.5 64.3 50.7 67.7 22.8 19.8 23.7 38.4 58.4 28.1 45.6 41.3 63.8 70.0 46.0 66.9 43.7 75.8 50.2 Captain Text S Captain Text M Captain Text L Captain Text XL 67.9 58.5 56.2 64.9 33.2 38.4 47.0 36.7 42.2 49.2 38.0 45.2 46.9 40.7 51.2 43.5 28.5 29.7 30.9 29.1 70.6 69.7 67.7 63.8 67.2 70.4 74.4 75.4 18.5 19.9 19.4 22.3 36.2 38.6 41.2 43.2 59.4 63.1 64.8 68.8 72.1 77.0 75.6 77.5 49.0 50.5 50.9 52.8 Doc T5 Query, Noguera et al. 2019 A. BM25 plus CE, Wang et al. 2020, Colbert v2, Santhanam et al. 2021, Splade v2, Formal et al. 2021, 71.3 75.7 73.8 71.0 32.8 29.1 34.9 35.0 34.7 31.1 33.8 35.6 46.3 33.4 33.6 47.9 34.7 27.1 26 52.7 Table 6. Comparison of Captain Text to previous methods on 11 zero-shot search tasks in the B evaluation suite, thatcontrastive et al., 2021. Results are reported both in the unsupervised data setting and in the transfer data setting. Captain Text outperforms previous best embedding methods, Ziering et al., 2020, Hofstadter et al., 2021, Isaac et al., 2021, in both the settings. In the unsupervised setting, BM25, Robertson, 2009, still achieves the best performance, while in the transfer setting Captain Text is competitive with methods that use substantially more compute at test time, Wang et al., 2020, Santhanam et al., 2021, Formal et al., 2021. Go Ruby Python Java JS PHP Average. Code BERT 69.370.6 Graph Code BERT 84.173.2 84.0 87.9 86.8 74.8 70.6 76.0 75.7 71.1 72.5 77.4 97.7 86.3 97.5 85.5 99.8 99.9 94.0 86.0 96.7 93.4 94.4 86.5 97.2 93.5 Captain Code S Captain Code M Table 7. Comparison of Captain Code on code search across 6 programming languages, Husain et al., 2020, with code BERT, Feng et al., 2020, and graph code BERT, Gyo et al., 2021. The task requires finding the relevant code block among 1K candidates for a given natural language query. Captain Code performs substantially better than previous methods on all the languages. Go Ruby Python Java JS PHP Average. Captain Text S 60.6 58.9 Captain Text M 65.4 63.1 92.6 91.4 48.4 52.8 47.6 60.1 47.9 53.5 43.1 60.7 Captain Code S 90.4 80.6 Captain Code M 90.0 89. 98.8 98.9 81.9 76.1 85.3 85.5 81.1 75.6 85.1 85.0 Table 8. Comparison of Captain Code vs Captain Text on large-scale code search, Husain et al., 2020. The task is to retrieve the relevant code block among 10K candidates for a given natural language query. It is interesting to note that Captain Text performs quite well on Python code search without explicitly training on text code pairs. Batch size 1536 12288 MR at 1071.4 84.7 Table 9. Performance of the Captain Text 300M model on NQ set given different training batch sizes. It al. 2021, by grouping samples within the same context, George I. et al., 2020, Isaac Ard et al., 2021, or by collecting data about the same object from different views, Tune et al., 2019. Learning word embeddings is a well-studied research area, Brown et al., 1992, Gutman and Hyvärinen, 2010, Mikuloff et al., 2013, Pennington et al., 2014. Learning low-dimensional representations of larger text pieces, denser than raw term-based vectors, has been studied extensively as well, Deerwester et al., 1990, Yi et al., 2011. Most of the recent models for learning sentence embeddings rely on supervised NLI datasets, using entailment pairs as positive examples and contradiction pairs as hard negatives. Zbert, Reimers and Gavike, 2019, trained a Siamese network to learn a representation where sentence similarity is estimated by the cosine similarity between embeddings. Lee et al., 2020, improves the embedding space to be isotropic text and code embeddings by contrastive pre-training performance training behavior 90 89 88 87 86 85 CentEval NQ STS 12 STS 13 STS 14 STS 15 STS 16 75 70 65 0 10,000 20,000 30,000 40,000 50,000 Training steps Figure 4. Performance of M1.2b, Captain Text Model on classification, search and sentence similarity tasks at different training steps. While the performance on search and classification improves with longer training, the performance on sentence similarity degrades. Via normalizing flows. The whitening operation is another alternative operation to improve the isotropy of the embedding space, Su et al., 2021. It is typical to initialize such models with a pre-trained language model, Devlin et al., 2019, before training on NLI datasets. Several methods have been studied for unsupervised or self-supervised sentence embedding learning, Legeswaran and Lee, 2018, Chang et al., 2020, Gao et al., 2021. Common approaches consider sentences within the same context as semantically similar samples, Quiroz et al., 2015, Legeswaran and Lee, 2018. To create positive training pairs with augmented samples, a diverse set of text augmentation operations have been explored, including lexicon-based distortion, Wei and Zhu, 2019, synonym replacement, Kobayashi, 2018, back translation, Fang and Zai, 2020, cutoff, Shin et al., 2020, and dropout, Gao et al., 2021. However, unsupervised sentence embedding models still perform notably worse than supervised sentence encoders. Large-scale text search based on dense embeddings and neural information retrieval, neural IR, have the potential to generalize better than keyword matching in classic IR systems. Neural IR systems encode documents at the indexing stage and then perform nearest neighbor search, Johnson et al., 2019, at query time, Lin et al., 2021. Neural IR models are usually learned by fine-tuning a pre-trained language model on supervised search corpus, Lee et al., Guu et al., 2020, Karpukhin et al., 2020b, Lewis et al., 2020. Many SOTA search models combine classical IR with neural IR in a staged setup, where the candidates are first narrowed down by BM25 keyword search, Robertson, 2009, and then re-ranked by joint query and document neural encoders, Noguera et al., 2019b, Question et al., 2021. Ziering et al., 2020, proposed ANTS, a contrastive learning framework for learning text representations for dense retrieval using mind-hard negatives. Other unsupervised retriever methods use the inverse closed task or masked salient spans to achieve significant improvement on ODCA tasks, Sachan et al., 2021. In comparison to most prior work, we find that with a large enough batch size, it is possible to achieve good search performance without using supervised data. Finally, the recently published Contriver, Isaac Ard et al., 2021, is most similar to our work on learning text embeddings for text search using contrastive learning on unlabeled data. Semantic code search refers to the task of retrieving code relevant to a query in natural language. The Code Search Net Challenge, Husein et al., 2020, presents a set of benchmark code search tasks in different programming languages, as well as a simple baseline model to predict embeddings of query and code via contrastive learning on a dataset of text, code, pairs. ContraCode, Chine et al., 2021, uses a contrastive learning task of identifying functionally similar programs, where the functionally similar samples are generated via source-to-source compiler transformations. CodeBERT, Feng et al., 2020, learns to predict semantic similarity with a pre-trained language model and graph code, but Gyo et al., 2021, further improves the performance on the Code Search Net benchmark by adding pre-training tasks on code structure. 5 broader impacts. Prior research has shown that text representation models encode the biases present in their training data, including those which are discriminatory towards protected groups such as Black people or women. Boluk-Basie et al., 2016, Kaliskan et al., 2017, May et al., 2019, Zhao et al., 2018, Rudinger et al., 2018. Biases encoded in embedding models may cause representational harms. 3. By reinforcing existent societal biases in the text corpus, and further propagating them in downstream tasks of embedding models. Therefore, we encourage further research on 2 research agendas: a. Developing robust evaluation methodologies for multiple classes of bias in training data and pre-trained models, and b. Developing and improving methods for mitigating encoded bias, including fine-tuning to reduce bias in pre-trained models. Kaliskan et al., 2017, May et al., 2019, Boluk-Basie et al., 2016, Liang et al., 2020, Park et al., 2018, Soleiman and Dennison, 2021. Until we have robust evaluation methodology, it is important to restrict and monitor the use of the model in downstream applications. Part 3. Representational harms occur when systems reinforce the subordination of some groups along the lines of identity, for example stereotyping or denigration. Crawford, 2017. Text and code embeddings by contrastive pre-training, particularly for those where risk of representational harm is great and those where biased representations may influence the allocation of resources and opportunities to people. Our embedding models are trained with large batch sizes and require substantial computation resources. While this training regime is environmentally and computationally costly, there are promising paths forward to amortize and offset these costs while allowing users to benefit from the capabilities of these models. For example, safe public access to large pre-trained language models, and efficient training pipelines that leverage improved model architectures and training schemes. We encourage further research and implementation efforts in these areas. 6. Conclusion: we showed that contrastive pre-training on unsupervised data with a sufficiently large batch size can lead to high-quality vector representations of text and code. Our models achieved new state-of-the-art results in linear probe classification, text search and code search. We find that our models underperformed on sentence similarity tasks and observed unexpected training behavior with respect to these tasks. Finally, we discussed the broader impact of our work on society. References: Bengio, Y., Corville, A. C., and Vincent, P. Representation Learning, A Review and New Perspectives. Transactions on Pattern Analysis and Machine Intelligence, 35, 8, 2012. Boluk Basi, T. Chang, K. Zhu, J. Y., Siligrama, V., and Kalai. A man is to computer programmer as woman is to homemaker. D. Beersing Word Embeddings. 29, 2016. D. Language models are few-shot learners. In Advances in Neural Information Processing Systems, 2020. Kaliskan, A., Bryson, J.J., and Narayanan. A semantics derived automatically from language corpora contain human-like biases. Science, 356, 6334 183186, 2017. Chen, M., Torek, J., Jun, H., Yuan, Q., De Oliveira Pinto, H.P., Kaplan, J., Edwards, H., Badar, Y., Joseph, N., Brockman, G., Ray, A., Guri, R., Kruger, G., Petrov, M., Klaff, H., Sastry, G., Mishkin, P., Chan, B., Gray, S., Ryder, N., Pavlov, M., Power, A., Kaiser, L., Bavarian, M., Winter, C., Tillit, P., Such, F. P., Cummings, D., Plapper, M., Chances, F., Barnes, E., Herbert Voss, A., Gus, W. H., Nicole, A., Pano, A., Tezak, N., Tang, J., Babushkin, I., Balaji, S., Chine, S. Saunders, W., Hess, C., Ka, A. N., Like, J., Akim, J., Misra, V., Morikawa, E., Radford, A., Knight, M., Brundage, M., Murati, M., Meyer, K., Wellinder, P., McGrew, B., Amodi, D., McCandlish, S., Sutskever, I., and Zaremba, W. Evaluating large language models trained on code. R14 preprint R14 2107.03374, 2021. Chen, T., Kinblith, S., Noruzi, M., and Hinton, G. A simple framework for contrastive learning of visual representations. In International Conference on Machine Learning, ICML, 2020. Chopra, S., Hadsell, R., and Lacan, Why Learning a Similarity Metric Discriminatively, with Application to Face Verification. In Computer Vision and Pattern Recognition, CVPR. IEEE, 2005. Canio, A. and Klo, D. Centival, An Evaluation Toolkit for Universal Sentence Representations. R14 preprint R14 1803.05449, 2018. Crawford, K. The Trouble with Bias. Keynote at NeurIPS, 2017. Bowman, S.R., Angeli, G., Potts, C., and Manning, C.D. A Large Annotated Corpus for Learning Natural Language Inference. In Conference on Empirical Methods in Natural Language Processing, EMLP. ACL, 2015. Dearwester, S., Dumas, S., Furness, G., Landauer, T., and Harshman, are indexing by latent semantic analysis. Journal of the American Society for Information Science, 41, 6391407, 1990. Brown, P.F., Della Pietra, V.J., D'Souza, P.V., Lay, J.C., and Mercer, R.L. Class-based N-gram models of natural language. Computational Linguistics, 18, 4467 480, 1992. Devlin, J., Chang, M.W., Lee, K., and Tautanova, K. Burt, Pre-training of deep bidirectional transformers for language understanding. In conference of the North American chapter of the Association for Computational Linguistics, NaturalQuestions. ACL, 2019. Brown, T., Mann, B., Ryder, N., Sabaya, M., Kaplan, J.D., Dariwal, P., Neelakantan, A., Shyam, P., Sastry, G., Atscale, A., Agarwal, S., Herbert Voss, A., Kruger, G., Hanayan, T., Child, R., Ramesh, A., Ziagula, D., Wu, J., Winter, C., Hess, C., Chen, M., Seigler, E., Litwin, M., Gray, S., Chess, B., Clark, J., Berner, C., McCandlish, S., Radford, A., Sutskever, I., and Amodi, Fang, H. and Zai, P. Cert, Contrastive Self-Supervised Learning for Language Understanding. R14 Preprint R14 2005.12766, 2020. Feng, Z, Gyo, D, Tang, D, Duan, N, Feng, X, Gong, M, Shou, L, Jin, B, Lu, T, Chiang, D, and Ju, M. Codebot, a pre-trained model for programming and natural text and code embeddings by contrastive pre-training languages. In Conference on Empirical Methods in Natural Language Processing, EMNLP, 2020. Formal, T, Lassance, C, Piwowarski, B, and Clinchant, S. Splade V2, Sparse Lexical and Expansion Model for Information Retrieval. R14 Preprint R14 2109.10086, 2021. Gao, T, Yao, X, and Chen, D. SimCSE, Simple Contrastive Learning of Sentence Embeddings. In Conference on Empirical Methods in Natural Language Processing, EMNLP, 2021. George I, J. M., Nitsky, O. Bada, G.D., and Wang, B. Dikaluta, Deep Contrastive Learning for Unsupervised Textual Representations. In Proceedings of ACL/IJKNLP, 2020. Goodman, N. 7 Strictures on Similarity. Bobbs Merrill, 1972. Gyo, D. Ren, S. Lu, S. Feng, Z. Tang, D. Lu, S. Ju, L. Duan, N. Sviatkovsky, A. Fu, S. Tufano, M. Deng, S.K. Clement, C.B. Drain, D. Sundaresan, N. Yin, J. Chiang, D. and Ju, M. Graph Codebot, Pre-training Code Representations with Data Flow. In International Conference on Learning Representation, ICLR, 2021. Gutman, M. and Hyvarainen, A Noise Contrastive Estimation, a New Estimation Principle for Unnormalized Statistical Models. In Conference on Artificial Intelligence and Statistics. PMLR, 2010. GUU, K, Lee, K, Tung, Z, Parjapat, P, and Chang, M. Realm, Retrieval Augmented Language Model Pre-training. R14 Preprint R14 2002.08909, 2020. Hadsell, R, Chopra, S, and Lacan, Y Dimensionality Reduction by Learning and Invariant Mapping. In Computer Vision and Pattern Recognition, CVPR, Volume 2, pp. 1735-1742. IEEE, 2006. He, K, Fan, H, Wu, Y, Zai, S, and Gershik, RB Momentum Contrast for Unsupervised Visual Representation Learning. In Computer Vision and Pattern Recognition, CVPR, 2020. Isaac G, Caron, M, Hosseini, L, Riedel, S, Bojanowski, P, Julin, O, and Grave, E towards unsupervised dense information retrieval with contrastive learning. R14 preprint R14 2112.09118, 2021. Jine, P, Jine, O, Chang, T, Abil, P, Gonzalez, J.E., and Stoica, I Contrastive Code Representation Learning. In Conference on Empirical Methods in Natural Language Processing, EMLP, 2021. Jia, C, Yang, Y, Xia, Y, Chen, YT, Parek, Z, Pham, H, Le, QV, Sung, Y, Li, Z, and Durig, T. Scaling up visual and vision language representation learning with noisy text supervision. In International Conference on Machine Learning, ICML, 2021. Johnson, J, Dowse, M, and Jaigu, H. Billion-scale similarity search with BUS. IEE Transactions on Big Data, 2019. Joshi, M, Choi, E, Weld, D, and Zettelmoyer, L. TriviaQA, a large-scale distantly supervised challenge dataset for reading comprehension. In Conference of the Association for Computational Linguistics, ACL. ACL, 2017. Karpuk Hin, V, Ugaz, B, Min, S, Lewis, P, Wu, L, Edunov, S, Chen, D, and Yi, WT dense passage retrieval for open domain question answering. In Conference on Empirical Methods in Natural Language Processing, EMLP, 2020. Karpuk Hin, V, Ugaz, B, Min, S, Wu, L, Edunov, S, Chen, D, and Yi, W dense passage retrieval for open domain question answering. In Conference on Empirical Methods in Natural Language Processing, EMLP, 2020b. Khosla, P, Tetawak, P, Wang, C, Sona, O, Tiun, Y, Isola, P, Maskiinat, O, Lu, C, and Krishnan, D. Supervised Contrastive Learning. R14 preprint R14 2004.11362, 2020. Kim, W, Sun, B, and Kim, I built Vision and Language Transformer without convolution or region supervision. In International Conference on Machine Learning, ICML, 2021. Hofstadter, S, Lin, S, Yang, J, Lin, J, and Hanbury, are efficiently teaching an effective dense retriever with balanced topic-aware sampling. R14 preprint R14 2104.06967, 2021. Kingma, D.P. and Welling, M. Auto-encoding variational Bayes. In International Conference on Learning Representation, ICLR, 2014. Hussein, H, Wu, H. Gazet, T, Alamanis, M, and Brockschmidt, M. Code Search Net Challenge, Evaluating the State of Semantic Code Search. R14 preprint R14 1909.09436, 2020. Kiros, J, Ju, Y, Salakhutdinov, R, Zimmel, R.S., Torlber, O, Ertesun, R, and Fiedler, S. Skip Thought Vectors. In Advances in Neural Information Processing Systems, NeuroPS, 2015. Text and Code Embeddings by Contrastive Pre-Training Kobayashi, S. Contextual Augmentation, Data Augmentation by Words with Paradigmatic Relations. R14 preprint R14 1805.06201, 2018. Kwiatkowski, T. Palomaki, J. Redfield, O. Collins, M. Parrick, O. Alberti, C. Epstein, D. Polosukhin, I. Kelsey, M. Devlin, J. Lee, K. Tautanova, K. N. Jones, L. Chang, M. W. Dai, O. Uskariot, J. Low, Q. and Petrov, S. Natural Questions, a benchmark for question answering research. Transactions of the Association of Computational Linguistics, 2019. Lee, K. Chang, M. and Tautanova, K. Latent Retrieval for Weakly Supervised Open Domain Question Answering. In Korhonen, O. Traum, Dr. and Marquez, L. eds. Conference of the Association for Computational Linguistics, ACL, pp. 6086-6096. ACL. Lewis, PSH, Perez, E. Pictus, O. Petroni, F. Karpukhin, V. Boyle, N. Kutala, H. Lewis, M. U. W. Rocktaskal, T. Riedel, S. and Klo, D. Retrieval augmented generation for knowledge-intensive NLP tasks. In Advances in Neural Information Processing Systems, NeuroPS, 2020. Lee, B. Chu, H. He, J. Wang, M. Yang, Y. and Lee, L. On the sentence embeddings from pre-trained language models. In Conference on Empirical Methods in Natural Language Processing, EMLP, 2020. Liang, P.P., Li, I.M., Cheng, E., Lim, Y.C., Salakhutdinov, R., and Morency, L. towards debiasing sentence representations. In Conference of the Association for Computational Linguistics, ACL, 2020. Lin, J. Noguera, R., and Yates, A Pre-trained Transformers for Text Ranking, BERT and Beyond. Synthesis Lectures on Human Language Technologies, 14, 41325, 2021. Legeswaran, L. and Lee, H. An Efficient Framework for Learning Sentence Representations. In International Conference on Learning Representation, ICLR, 2018. Liu, J. Batra, D. Parrick, D. and Lee, S. Vilbert, Pre-training Task-Agnostic Visual-Linguistic Representations for Vision and Language Tasks. R14 preprint R14 1908.02265, 2019. Nguyen, T. Rosenberg, M. Song, X. Gao, J. Tiwari, S. Majumdar, R. and Deng, L. MSMARCO, a human-generated machine reading comprehension dataset. R14 preprint R14 1611.09268, 2016. Noguera, R., Lin, J., and Epistemic, O. From Doc to Query to Doctquery. Online preprint, 2019a. Noguera, R., Yang, W., Joe, K., and Lin, J. Multistage Document Ranking with BERT. R14 preprint R14 1910.14424, 2019b. Park, J. H., Shin, J., and Fung, P. Reducing Gender Bias in Abusive Language Detection. In Conference on Empirical Methods in Natural Language Processing, EMLP, 2018. Pennington, J., Soka, R., and Manning, C. Glove, Global Vectors for Word Representation. In Conference on Empirical Methods in Natural Language Processing, EMLP, 2014. Peters, M. E., Newman, M. Ear, M. Gardner, M. Clark, C. Lee, K. and Zettelmoyer, L. Deep Contextualized Word Representations. In Proceedings of NGIL/IJKNULP, 2018. Question, y, ding, y, lu, j, lu, k, ren, r, jiao, x, dong, d, wu, h, and wang, h. Rocketka, an optimized training approach to dense passage retrieval for open domain question answering. In Conference of the Association for Computational Linguistics, ACL, 2021. Radford, A, Kim, J. W., Halasi, C., Ramesh, A, Go, G. Agarwal, S., Sastry, G. Atscale, A, Mishkin, P. Clark, J. Kruger, G. and Sutskever, are learning transferable visual models from natural language supervision. R14 preprint R14 2103.00020, 2021. Raffle, C. Shazier, N. Roberts, O. Lee, K. Narang, S. Maitena, M. Ju, Y. Lee, W. and Lu, P.J. Exploring the limits of transfer learning with a unified text-to-text transformer. R14 preprint R14 1910.10683, 2019. Ramesh, A. Pavlov, M. Go, G. Gray, S. Voss, C. Radford, O. Chen, M. and Sutskever, I. Zero-shot text-to-image generation. R14 preprint R14 2102.12092, 2021. May, C. Wang, A. Bordia, S. Bowman, S.R., and Rudinger, R. On measuring social biases in sentence encoders. In Conference of the North American Chapter of the Association for Computational Linguistics, NaturalQuestions, 2019. Reimers, N. and Gavike, I. Sentence-BERT, sentence embeddings using Siamese-BERT networks. In Conference on Empirical Methods in Natural Language Processing, EMLP, 2019. Mykhalaf, T. Chen, K. Karadu, G.S., and Dean, J. Efficient Estimation of Word Representations in Vector Space. R14 preprint R14 1301.3781, 2013. Robertson, S. The Probabilistic Relevance Framework, BM25 and Beyond. Foundations and Trends Register Trademark Symbol in Information Retrieval, 2009. Text and Code Embeddings by Contrastive Pre-Training Rudinger, R. Narodowski, J. Leonard, B. and Derm, B.V. Gender Bias in Conference Resolution. R14 preprint R14 1804.09301, 2018. Sachan, D.S., Paitwary, M. Shuabai, M. Kant, N. Ping, W. Hamilton, W.L., and Catanzaro, B. End-to-end training of neural retrievers for open domain question answering. Inzong, C. Xia, F. Lee, W. and Navigli, R. eds. Proceedings of ACL/IJKNULP, pp. 6648 6662. ACL, 2021. Santhanam, K. Kotab, O. Sardfolkan, J. Potts, C. and Zaharia, M. Kolbev 2, Effective and Efficient Retrieval via Lightweight Late Interaction. R14 preprint R14 2112.01488, 2021. Shroff, F. Kulnishenko, D. and Philbin, J. Facenit, a unified embedding for face recognition and clustering. In Computer Vision and Pattern Recognition, CVPR, 2015. Shen, D. Zheng, M. Shen, Y. Question, Y. and Chen, W. A simple but tough to beat data augmentation approach for natural language understanding and generation. R14 preprint R14:2009.13818, 2020. Soka, R. Pereligin, A. Wu, J. Chuang, J. Manning, C. D. Ing, A. and Potts. See recursive deep models for semantic compositionality over a sentiment tree bank. In Conference on Empirical Methods in Natural Language Processing, EMLP, 2013. Son, K. Improved Deep Metric Learning with Multiclass N-pair Loss Objective. In Advances in Neural Information Processing Systems, NeuralQuestions, 2016. Soleiman, I. and Dennison, C. Process for Adapting Language Models to Society, PALMS, with Values-Targeted Datasets. R14 preprint R14 2106.10328, 2021. Su, J, Cao, J, Lu, W, and OU, Y. Whitening Sentence Representations for Better Semantics and Faster Retrieval. R14 preprint R14 2103.15316, 2021. Sun, C. Myers, A. Vondrick, C. Murphy, K. and Schmid, C. VideoBert, a joint model for video and language representation learning. In International Conference on Computer Vision, ICCV, 2019. The K, N, Reimers, N, Arukal, A, Srivastavat, A, and Gavik, IB, a heterogeneous benchmark for zero-shot evaluation of information retrieval models. In Advances in Neural Information Processing Systems, NeuralQuestions, 2021. Tiun, Y, Krishnan, D, and Isola, P. Contrastive Multiview Coding. European Conference on Computer Vision, ECCV, 2019. Van den Oord, A, Die Lemon, S, Zen, H, Simonian, K, Vinyals, O, Graves, A, Kalkbrenner, N, Senior, A, and K. Vukkyoglu, K. Wavenit, a generative model for raw audio. R14 preprint R14 1609.03499, 2016. Van den Oord, A, Lee, Y, and Vinyals, O. Representation Learning with Contrastive Predictive Coding. R14 preprint R14 1807.03748, 2018. Vaswani, A, Shazier, N, Pummer, N, Uzkariat, J, Jones, L, Gomez, A. N, Kaiser, Lu, and Polosuk-Hin, I. Attention is all you need. In Advances in Neural Information Processing Systems, NeuralQuestions, 2017. Verveek, J, Lilligrap, T.P., and Richards, B. A Relevance Realization and the Emerging Framework in Cognitive Science. Journal of Logic and Computation, 22, 179.99, 2012. Wang, W, Wei, F, Dong, L, Bao, H, Yang, N, and Zhu, M. Minilm, Deep Self-Attention Distillation for Task-Agnostic Compression of Pre-trained Transformers. R14 preprint R14 2002.10957, 2020. Wei, J.W. and Zhu, KEDA, Easy Data Augmentation Techniques for Boosting Performance on Text Classification Tasks. R14 preprint R14 1901.11196, 2019. Williams, A, Nangia, N, and Bowman, S. A Broad Coverage Challenge Corpus for Sentence Understanding Through Inference. In Conference of the North American Chapter of the Association for Computational Linguistics, NARCL. ACL, 2018. Wu, Z, Zhang, Y, U, SX, and Lin, D. Unsupervised Feature Learning via Nonparametric Instance Level Discrimination. In Computer Vision and Pattern Recognition, CVPR, 2018. Zirang, L, Zirang, C, Li, Y, Tang, K, Lu, J, Bennett, PN, Ahmed, J, and Overwijck, are approximate nearest neighbor negative contrastive learning for dense text retrieval. R14 preprint R14 2007.00808, 2020. Yi, W.T., Tautanova, K, Platt, J.C., and Meek, C. Learning discriminative projections for text similarity measures. In Conference on Computational Natural Language Learning, CoNLL. ACL, 2011. Zbontar, J, Jing, L, Misra, I, Lacan, Y, and Denai, S. Barlow twins, Self-Supervised Learning via Redundancy Reduction. In International Conference on Machine Learning, ICML, 2021. Zhang, Y, He, R, Lu, Z, Lim, KH, and Bing, L. An unsupervised sentence embedding method by mutual information maximization. In Conference on Empirical Methods in Natural Language Processing, EMLP, 2020. Text and Code Embeddings by Contrastive Pre-Training Zhao, J, Wang, T, Yateska, M, Ordonez, V, and Chang, K. Gender Bias in Conference Resolution, Evaluation and Debiasing Methods. R14 preprint R14 1804.06876, 2018.